Good afternoon. We resume our discussion of design of experiments. This is part of our this special sequence of lectures on Six Sigma that we are conducting for you. I have been discussing the simpler methods for conducting designed experiments, factorial experiments, and also the data analysis method that is used for it. I discussed a simple method, which is basically adding and subtracting certain numbers, and you'd end up with the main effects and what we call the interaction effects. If you look at the slide, if you look at what we began with, we had various types of factors involved. Some of those we decided to include in our experiment. We had the type of driver involved in this golf game. We had the different types of balls involved. We had walking versus riding, and also the kind of drinks we were using while you're playing our golf. Then there were these time of round. Was it in the morning that we're playing this game? Or was it at lunchtime, after lunch, or was it in the evening? What was the weather like, and was it changing during the day? The type of golf spike we used, that also could affect the score of the thing. And there are many, of course, many other factors, the nature of grass and so on and so forth, that also might be affecting your score. And you wanted, of course, as a good golf player, you wanted to keep your score as low as possible. Now, getting a low score is the game, is really the goal of playing golf. Now, it could be affected by some external factors. Of course, a big one is my own skill in hitting the ball and getting it in the hole. The other is the effect of any of these factors, the driver, the ball, the walking versus riding, or the type of beverage. Now, suppose we are not controlling these other factors, but they are changing. They are the nuisance factors. They are changing as time progresses. So let me show that to you, show this total picture in the form of a cause and effect diagram, the fishbone diagram. The effect, of course, is my score, golf score. That's my response. And what are some of the control factors? Let's list out some of the control factors. The one that we have decided to use in our experiment, those are going to be the driver, this is the stick with which you hit the ball, and of course the ball type. This is also going to be one of those variables that you might like to optimize as you're playing golf to try to keep your score low. Then walking versus driving. This could be another factor. And of course, the drink that you're using. So, drink. But like I said, there are many other factors that we have ignored, that we have left out of the thing there. And I'm going to put them down as noise factors. These might also be affecting my score. And this could be weather. This could be the kind of spike I used. This could be the time at which the game is played, and so on and so forth. There are many other factors perhaps. And these are not, we are not controlling. These are going to be the noise factors. The result is going to be, instead of getting a very sharp score every time I play a round of golf, I'll end up with a variation there. So what would this variation be like? This variation, I can probably draw a picture of it. It would be a variable quantity like this. So instead of getting a sharp score like this, I'll not be getting a sharp score like this. This will not be the one that I'll be observing. I'll be actually seeing some variation. This variation is what we'll be observing. If I played many different rounds, my scores would be varying all over the place here. Now this is going to be possible then at any of these corners. Go back to our diagram again. It could be that I'll end up with a variation here. I'll end up with a variation here. I'll end up with a variation here. Also, I'll end up with a variation here. So instead of getting one sharp number, I'll end up with a set of data that will show some variation. In the presence of such variation, can I still find whether changing the ball type or changing the driver or changing my drinking material or walking versus riding, can I say with some confidence that I can still say that playing with ball type B is going to be better than playing with ball type T. I'll score less with ball type B. How do I do that in a noisy environment? How do I really do this in this noisy environment? Look at the noisy environment. And my response is going to be like this. Can I still say, is there any method available that can now look at this kind of data? It can still give me some information about the effect of the ball type or driver or walking and drinking and so on, while these noises are all going to be active. That technique, of course, is called ANOVA. And I'm just going to write it down. First, I'm going to write it down very clearly here so you'll see what that technique is. ANOVA stands for Analysis of Variance. This is a very important statistical technique. It looks at variable data like this, and then it tries to see, does ball have an effect that is significant when I compare that to the effect of noise, or does driver have an effect that is significant when again I compare that to the effect of noise, the background noise. That is actually all this is done by this technique of ANOVA, and this is going to be the subject of this hour's talk. I start by saying it's a method to estimate different components of variance. Now, variance components are being caused now by these different experimental factors. They will cause a variance to the mean score from the average. So, some may try to reduce that score, some may try to increase that score. Each factor setting is now going to cause a variance in that response there. We'll be constructing what we call a test statistic, and we'll be comparing that test statistic as to check whether or not the effect of a particular factor or the interaction between 2 or 3 factors is that significant when I compare that to the background noise. This is going to be our approach in the ANOVA method. So different types of experiments actually will have different types of effects underlying, and therefore we'll have different statistical models that will be utilized for different types of experiments, and we'll see examples of some of them. And again, we have the fixed situation and we got the random factor situation. And of course, our goal is going to be to try to perform some statistical test on the data that we work out, that we figure out. And we'll begin all of this using the single factor experimental statistical model. That's the one we'll be using. So in place of having all of these things being active together, we'll basically look at the effect of maybe perhaps only ball type. Perhaps this is the one we'll be focusing on. This is the one we'll be focusing on. We'll try to see if I treat everything else as noise, all the other factors as noise, if I treat all of this as noise, can I see in the response, can I see the effect of changing ball type? Can I see that? Can I see that effect there? This is what we would like to be able to do using this technique called ANOVA. Let's see how we go about doing that. One thing I have to do is I have to make sure that I have more than 2 settings available. That means like more than 2 ball types available. This makes the statistical analysis easy and straightforward. This is something I would like to be able to do. And here's an example. It's a little complicated example. This lecture, by the way, is going to be more complicated than what we've done so far, that we've already in the past hour. This one is going to be looking at some engineering systems, and also the data analysis method is going to be more fancy, and please be prepared for it because it's going to be a little more complicated than what we've done so far. Again, if I draw the cause and effect diagram for this system, I have the effect, and the effect is going to be, in this case, we are interested in an engineering system and would like to be able to see the effect of certain process factors. These are going to be engineering process factors on itching. I should tell you something about this process. You know, most of these electronic devices, like for example this one, this digital watch for example. This digital watch has chips inside, and those chips contain transistors and other semiconductors. And these are of course not fabricated by using soldering guns. It is not done that way because this is at a very micro level, very tiny level. So here what we do is we come up with a substrata, and that's made of silicon. On that we deposit various types of foreign elements, and these elements are brought in as gases and they're etched on the surface, and the result is we end up forming what we call junctions or juxtaposition of 2 different sets of materials and so on, by diffusing certain amounts of other materials such as antimony and arsenic and so on, those are diffused into the substrata, which is made of silicon, and thereby we form these transistors. Now this process requires a controlled environment, and a lot of conditions, they are changed when you're trying to do this. So if you look at the system, if you look at the physical system where we produce these silicon joints, they turn out to be an environment that is very well controlled and very precisely controlled, so you get the right amount and the number of junctions formed, and a lot of physical properties and electronic properties have to be there. They also have to be ensured when you're trying to come up with the chips that go inside these digital watches, and a lot of other solid state devices, for example. Now what we are going to be looking at is, we're going to be looking at the RF power. This is the radio frequency power which is applied on the system. So that's going to be one process variable. So I'm going to be putting that down here as a process variable, and that's going to be RF power. RF power. That's going to be my process variable. Everything else in the system is going to be treated as noise. There may be a whole bunch of other factors that also could be affecting this etching quality, but I'm going to be treating all of them as noise. So these are all going to be noise factors. I'll be interested in knowing whether changing the settings of this RF power, does that become statistically visible when I look at the effect in the presence of this noise. So the noise is going to be there. My goal is going to be to try to understand whether if I change these RF settings at different levels, and what are those levels? I've been given certain levels: 160 watt, 180 watt, 200 watt, and 220 watt. Notice here, I'm changing them. So I'm changing, basically what I'm doing here is I'm changing these settings. So RF power is changing as I go this way. Does that produce an effect on this? Does that produce an effect on this? And I've got to find this out in the presence of noise. In the presence of this noise, I'm going to be finding this out. And like I said to you before, this technique is called ANOVA. The technique that allows you to do this is called ANOVA. So you can see this is a pretty powerful method. It looks at a noisy background, and in spite of that noise being there, it tries to tell you whether or not changing the settings, and these are called treatments, of a certain factor on this thing, if this is significant. When you change the settings, when you change the treatment of this particular factor, this is one experimental factor, does that actually show up here? And can you tell that there is an impact when I change power from 160 to 180 to 200 to 220? Does that actually show up here? When this itself is variable caused by these noise variables. This response itself is variable. And I would like to be able to tell that. I'd like to be able to tell this, in fact, in the presence of noise. I'd like to really know whether RF power really, changing RF power really has an effect. Does it shift the process in any way? Does it shift that etching response in any way? Now, because this noise is going to be there, we are going to be replicating the experiment. So whatever I do, at each of these settings, I'll be doing 5 replications. I'll be doing 5 replications in order to make sure that this noise thing does not fool me. It's not that it is high when I'm running at 160 and it's low when I'm running at 200, for example. That chance should not be left to nature. We're going to be randomizing, and also we're going to be running 5 replicates at each setting. This is what we'll be doing. Then of course we'll be doing our averaging, and we'll be doing the statistical data analysis to be able to say whether or not that factor had an effect. Let's see how we go about doing that. First of all, on the screen, I show you the results. Which is the effect of etching. The etching that I produced on those silicon wafers. And I've got 5 replicates of each. When power setting was 160, I got 575, then I got 542, I got 533, 530, 539, 570. And the average turned out to be 551.2. When I change power setting to 180, I got an average of 587. When I change it to 200, I got an average of 625. And when I put power setting at 220 and I conducted 5 trials, I ended up with an average of 707. These are the effects that are turning out to be measured in the on that etching. Etching is really the process effect that I would like to be able to see. If you see it on another way, that etching actually is showing up as a little band here at 160. Notice here, there is of course a mean value there, but there is a band, there is a variation there. There is of course a band of variation in response. There is a band at 180, there is a band at 200, there is a band at 220. These bands, these are variances that have been caused because all the different noise factors which actually also changed when I was replicating my experiment. So because of that, I end up with these little bands there in all these 4 settings there. In the presence of such variation, can I still say that changing power had an impact on response? Can I say that? And I would like to be able to say that with a certain level of confidence. This is what I would like to bring in statistics. I'd like to conduct a statistical data analysis. Let me give you the framework for this data analysis. Treatment levels are like those 4 settings that I had: 160 watts, 180 watts, 200 watts, and 220 watts. Here, let's say that I've got 1, 2, 3, 4, up to small a, little a, different levels of treatment. And I have replications which go from 1 to n. These are replications possible. And the average here is going to be y1 bar is going to be the average response noted at treatment level 1. There is only one factor that is being varied from one factor that has been called A, factor A. It's being changed from 1, 2, 3, changed through these number of settings there, 1, 2, 3, 4, 5, 6, 7, 8, up to A, little a. The averages turn out to be y1 bar here, y2 bar here, y3 bar, and so on. I've got ya bar, ya dot bar there. The overall average is going to be y bar double dot. That's going to be the average of everything. How many data points do I have? I have A this way and I have n this way. So A times n is the total number of data points I have. In fact, that is the total number of runs I made when I conducted this experiment. This involved only one factor at A different levels. So one factor, the treatments changed from 1 to A, little a different levels, and each trial was replicated n times. So I've got A times n. This is the total number of trials I've run in doing this experiment. That's what I've gathered. This is the data on which I'll be performing my statistical analysis. Let's see how we go about doing this. This is of course a completely randomized experiment, and I mentioned to you I have to randomize whenever I'm not controlling noise factors, and noise factors themselves, they may actually impact, they may end up impacting the outcomes. I will probably construct a little model there. So I've got my response. And the response in the etching case was this RF power would be factor A. This RF factor is my factor A. And I've got my response here. Response is going to be measured as Y. Y is the response there. Therefore, I can really write here Y, and let me use a different color pen here. Y is the effect, ith treatment, jth replication. This is equal to, there is an overall average. There is an overall average which I'm going to call mu, plus there is going to be an effect due to the treatment which I'm called tau I, and there is going to be a random component, random effect due to all the other factors which I'm not controlling. This I'm going to call ij, because this is going to change from run to run. These tau I levels actually, they are coming from when I'm changing my setting for this factor A from 1 to A. So there are A different settings that are possible, and I've got this. So I here is going, just note this down, I here is going from 1 to little a, and j is going from 1 to little n. And I've got a total of then a times n trials. I've got yij, n different, a times n different values of this. Each will be this thing. Now this is my model. This is going to be my theoretical response model. I'm just going to write this down as response model assumed. Is this. This is my response model assumed. There is an overall average response. There is the effect due to treatment of RF power, which is the factor I'm changing. And of course, anything else that does not get changed contributes an error. We call this error. And this is coming at, for each reading, for each trial, I'll end up with a EIJ, epsilon ij component. That's going to be the error term there. So this is what I'll be calling actually the error term, the background noise. If I do that, if you come back to my slide again, you'll notice here, I've got the model there, yij equal to mu plus tau I plus epsilon ij, I varying from 1 to a, j varying from 1 to n. Mu is the overall mean, tau is the ith treatment effect, epsilon ij is the experimental error, and this is assumed to be normally distributed with a mean 0 and some background variance which we call sigma squared. This is supposed to be relatively small, but it's acknowledged to be there, and it is there. This model now defines how the response is going to change when I change treatment. If you look at the total variability, what is the total variability? It is actually, if you look at our quantities are these yij. So at some point here, something will be called yij. That is the response of my treatment being at level I and my replication number being at j. The difference between yij and this grand average, there's going to be a delta there. What is this contributed by? What is this difference attributable to? One is, of course, the treatment variation. The other is the effect of noise. Both of them, they contribute to the variation that exists between yij, which is here, and the overall average. And this is exactly what you'll see when you see the variation there. Now, this is my delta. This is my deviation. This is the deviation of the ijth data point, yij, minus the overall average. I square them because sometimes this delta, this deviation may be plus, sometimes it may be minus. So to sum them all, I end up with this summation. First it is done over the replication, then it is done over the treatment levels. I've got yij minus y bars whole square. This thing is squared. That is my sum total. When I sum them up, I end up with my total sum of squares. This is a very important quantity, and this is really the overall variation that exists in the data. That is there. Now this is contributed by two components, one of which comes from the experimental factor, my factor RF, my factor there. This is contributing one component. This will be the treatment component of the total variation that will be contributed by this. Then of course is the noise. All these noise factors, they are also contributing a component. This is going to be those little epsilons. This is called the sum of squares due to errors. So if you come back to the slide again, you'll find that this total variation here can be split up algebraically between two components. One is the sum of squares of deviations due to treatment effects, and the sum of squares due to errors, which is like any other factor that might also be affecting the process. The sum total variation is the summation of sum squares of treatments and the sum squares of errors. This result, by the way, was found by Sir Ronald Fisher in the 1940s. He's the one who he worked out this algebra for the first time. And that was a very, very important contribution because it let us separate out the effect of the experimental factor from the rest of it. I looked at this total variation. Ronald Fisher actually looked at this total variation and he was able to split it out mathematically between the contribution due to this treatment factor, the experimental factor, and the rest of it. This component is called sum of squares due to treatment, and this contribution, this component of the total variation there is called the sum of squares, error sum of squares. That's what this is. These two, the sum of squares due to treatment and error sum of square, they together constitute the ANOVA analysis, and we'll see how that is done. So in fact, Ronald-Fisher's identity is shown here, and again you can see that sum of squares due to treatment plus sum of squares due to the errors, these together they form the total sum of squares, and that's what is shown here. Now what we do is we set up a statistical hypothesis. This comes under the notion of statistical test of hypothesis, and our hypothesis is going to be treatment has no effect. Varying RF power has no effect on basically the etching. Basically, initially, now this is going to be our initial hypothesis, which is just a guess, a speculation. What we are saying is, initially we will assume that this RF power contribution contributes no variation to etching. That's going to be our H0 or the null hypothesis. The alternate, of course, is going to be at least one of these settings produces a deviation that is different from what is produced by the other effects there. At least one of them produces an effect that is going to be significant when I compare that to what we call background noise. So in fact, H0, which is your null hypothesis, turns out to be mu1, which is the effect due to first treatment, second treatment, mu2, third treatment, and so on, up to mu a. We assume that all of those treatment effects are going to be equal, and H1 is the alternate. This is H0. H1 is the hypothesis that at least one of those means is different. So now I've got to do some data analysis. I've got to do some calculations using these sum of squares due to errors. And these have been produced. These have been produced by our data analysis, data measurements, and so on. I'll be testing the acceptability of this hypothesis that treatment errors indeed are absent. How do I do that? For that, I need another quantity called the degrees of freedom, because it turns out that sum of squares by themselves, they are really not comparable unless we convert them into what we call mean sum of squares. Mean sum of squares turn out to be comparable to what we call variance. Mean sum of squares are the sum of squares divided by degrees of freedom, or degrees by divided by the appropriate sample size. Just like we have sample variance, we've got the total sum of squares from the estimated mean, and I divide that by sample size minus 1. I do the same sort of thing when it comes to calculating my mean sum of squares. So the mean sum of squares due to treatments is going to be sum of squares due to treatment divided by its own degrees of freedom, and the mean sum of squares due to errors is going to be sum of squares due to errors divided by its own degrees of freedom. How did I find the error degrees of freedom? How did I find that? Well, I've got this total degrees of freedom. Now the total number of data points we had was a times n. Why is the total degrees of freedom a times n minus 1? Well, it turns out that in order for me to find all the different deviations, I had to find at least one quantity. I had to measure at least one quantity in the data, from the data, that I then used to find all the different deltas, all the different deviations. That one quantity is going to be the overall average, the y bar dot dot. The y bar dot dot is the quantity. Let me show you where it stands. The y dot dot bar is standing right there. So that is the quantity that I calculated in order for me to find all the deviations, all the different deviations. I had to find this quantity. Because I've done that, I've lost 1 degree of freedom, and that's why the total degrees of freedom available to me is an minus 1. Then of course I've got the treatment sum of squares, and I've got its corresponding degree of freedom. That turns out to be a minus 1, because again, one of the treatment, because the sum of all the treatments is basically 0. One of those turn out to be in fact dependent on the rest of them. And in fact, it turns out that's what forces you to lose 1 degree of freedom. So I have got 1 degrees of freedom lost here. I've got treatment degrees of freedom turn out to be a minus 1. And if you subtract a minus 1, if we subtract this quantity a minus 1 from a n minus 1, you're left with what we call error degrees of freedom. That's what I've got there. Now I'm able to calculate these quantities, the mean square treatments and the mean square errors. I'm able to compare these two quantities. Now let me talk about this a bit intuitively. We can go back to our picture here. It turns out, suppose indeed RF power had no effect whatsoever on etching. Suppose it had no effect. Then the effect that we would measure here would be affected by all these noise factors. So in fact, it turns out if RF power had no effect whatsoever on the response, we'd probably find the mean sum of squares due to treatments, which is like mean deviation that I produce, sum of all the deviations that I produce by varying the experimental factor over this full range of treatments. It would turn out that mean sum of squares should be comparable to what we have here from the errors. And the ratio of mean sum of squares due to treatment and mean sum of squares due to errors should be something like approximately equal to 1. Mean sum of squares due to treatment divided by mean sum of squares due to error. This ratio should be of the order of 1 if mean sum of squares are not significant. If there is no treatment to treatment variation, then between two readings it would be of the same order as just plain simple error in experiments. When I do that, I end up with a ratio, and that ratio, it turns out, to be an F distribution. And I'm going to be skipping some of these slides. You can see them in the text. These are going to eventually lead you to the estimation of an F factor. And that F factor is summarized on this analysis of variance table. And what does this show to us? It makes a summary of, first of all the different sum of squares, their degrees of freedom, and the mean treatments. And the columns here, the first column is the sum of squares due to treatments. This is going to be between treatments. And the error sum of squares, this is within treatment. Within one treatment, as I go from 1 to n, when I replicate the experiments, at the same treatment level, the variation that I ought to see is due to the errors only. And that's what turns out to be here. The error is within treatment. Within a treatment, I'll have this sort of variation there. That turns out to be SST, sum of squares total minus sum of square due to treatment. And the corresponding degrees of freedom is shown here. And of course, from this I can calculate my mean square error. And of course, this is going to be my test statistic. My test statistic is going to be the ratio of mean squares, sum of square due to treatment divided by and the mean sum of squares due to error. Mean sum of squares due to treatment divided by mean sum of squares due to error. This turns out to be F calculated. It turns out this being a ratio of two chi-square variables or two variances. This being the ratio of two variances or two chi-square variables, it has the F distribution. And because it has the F distribution, I can then go back and do my test of hypothesis. This right hand side is coming from a table. And this table actually allows for a certain amount of type 1 error in test of hypothesis. I use my calculated ratio. I compare that to what we call the critical value at the chosen level of significance, which is at the chosen level of type 1 error, which is alpha, for the appropriate degrees of freedom, which is a minus 1 and a times n minus 1. If this quantity is bigger than this quantity, that means my ratios are this ratio, means sum of squares due to treatment and MSE. This ratio is greater than the critical value. And if it is greater than the critical value, I'll be rejecting the hypothesis that mu1 equal to mu2 equal to mu3 equal to mu4 equal to mu a. This hypothesis I'll be rejecting. In fact, what I'll be saying is that changing RF power did in fact impact the response, which is etching there. So changing RF power, this is initially what we started out to do. We changed the treatment levels. We went from 160 watt. Look at the picture here. We looked at 160 watt. Then we changed the setting to 180. Then we looked at 200. Then we looked at 220. And each time we did this, we kept looking at our etching. And of course, we replicated the trials. Each time treatment was changed, we replicated the trials, and I ended up with my data there. Then to find out whether or not the variation here is as caused by these treatments, whether it is significant when I look at the variation that is caused by noise only, that is this test statistic, and that turns out to be this F quantity there. If this F quantity is greater than the critical value of that F quantity for the same degrees of freedom and the level of type 1 error that is acceptable to me, I'll say that treatments indeed had an impact. What happened in this case there? Remember the data that I showed you? Let me just show you the data again. This was my experimental data, and my experimental data was like this. This was my experimental data. Just by looking at this data, we could not really say whether or not treatments had an effect. But when I converted this data into an ANOVA table, the ANOVA table looks like this. This is the ANOVA table for the same example. Lo and behold, I find a value of F naught, which is the ratio of the mean sum of squares caused by RF power divided by the error mean sum of squares. That turns out to be quite large. In fact, this is considerably large when you compare the critical value of it. The critical value, as I show in this picture here, is quite small. The critical value at 5% alpha level is here. The critical value at 1% alpha level is here. And the calculated value of F, which is the ratio of the mean sum of squares due to treatment and the mean sum of squares due to error, that ratio is 66.80, which is much bigger than the quantities that would, that would allow me to accept the hypothesis that indeed treatment levels had no effect at all. So this is a very, very powerful method, and it's a method that is, that works even in the presence of all the different noise that is there. Notice here all the different noise. All these red factors, they are causing their own disturbance there. But what I've been able to do with the F test is, I've planned my trials in such a way that I take replicated experiments. I take replicated readings at each of these treatment settings. I calculate the total sum of squares. I split it up into the part that is caused by the treatment, and whatever remains is the error sum of squares. I work out the mean treatment sum of squares, and I work out the mean error sum of squares. I look at the ratio of those two. That's my F test statistic. I compare the F test statistic on this diagram. On this diagram, I compare that, the calculated value, I compare that to the critical values, critical theoretical values of my F. This is way to the right hand side, which is like really in the rejection region, and therefore I would say that RF power indeed has a significant effect on itching. That's like one of the things I wanted to establish empirically. I should again go back a little bit and tell you that such results are not possible to be obtained even at this time using only theory. Theory cannot tell us this. We have some empirical models that can tell us this. But if we come up with a new process and we've got new factors involved as far as these process factors are concerned, as far as noise factors are concerned, you end up with some new factor there, new thing there, which will be true for any new R&D process. If you do an F test, if you do ANOVA, and if you do an F test, you'll be able to say with some confidence that yes, changing a particular design factor or a process factor has a significant effect on the output. There are certain tests that you could do, and I'll just give you an example of some of the tests there. One of the things is take a look at the errors. And what are errors? Errors are the observed value minus the model value. The model value was the response that we saw. If I would bring up the model value again, first of all, let's just go back and see where I got these error measurements from. Let me first show you what these model values are. The model values are exactly what we began with, and I'm just going to show you the model. The model is going to be right here. This is the model. Notice this is the model. I've got an overall mean, then I've got the treatment effect, then I've got the error effect there. The model assumes that these errors are normally distributed, they have zero mean, and they've got some small variance. This is my model. This is my model, and this is going to be the representation of a model at treatment setting I at replication number j. That's what is this model like. Now, of course, I've got an actual observation. So the model will assume that the response is going to be mu plus Ti. This is going to be assumed to be expected value of this is 0. So the expected value of this quantity for the ith treatment is going to be mu plus tau I. That's what I use as my model, and when I evaluate my errors, I have here mu plus tau I. Mu is the overall mu average plus tau I. This is going to be my expected value of my of the response at my treatment level, and the error is going to be now the difference between these two. I have here a quantity that is the error quantity. The error quantity is going to be the difference between the observed value of y minus the value that is predicted by y. This is the true error. Now, one of the assumptions that the ANOVA method makes is that these errors, if a model is done well, if the model has been constructed well, which is like this y hat ij, if this has been constructed well, the errors are going to be normally distributed and they will be visible like this as a straight line on a normal probability plot. If you produce a normal probability plot of the errors, it will turn out to be straight like this. And of course, variance also is going to be small, so that's also something that we could do. These are some of the tests that are done on the errors before you accept the results of the ANOVA, of an ANOVA. And this is quite easy to do once you got your, there are some other tests also available, and those can be looked at. Let me spend a few minutes to show you one example where you will be able to see, for example, what other use can basically design of experiment be put to. I'm just going to roll off to a point when I come back to a method called response surface method. That's going to be a pretty powerful method in optimizing a function. Let's see how design of experiments are used there. The response surface method turns out to be one of those methods which is used directly empirically. You conduct experiments and you study the response. What we did in the case when we are looking at, for example, we're looking at ANOVA, or we're looking at some of the other ones. For example, when we look at that golf game there, we changed the settings of the control factors at discrete levels. Now, what we really like to be able to do is when we look at the response, and you'll see that in a couple of minutes, you'll see what we mean by the response of a particular process. The response itself may turn out to be a very crazy function. And if you're trying to optimize the process, if you're trying to reach the peak of the response surface that is there, certain special methods have to be utilized there. Certain special design schemes or experimental schemes also have to be utilized. I'm going to give you a glimpse of that. I'm just going to give you a glimpse of it because later on you can pull up a textbook and study this technique called RSM, response surface method, and that will help you empirically optimize different processes. So what are some of the methods now that we'll be utilizing? We'll be focusing right now on RSM, the response surface method for optimizing a procedure. If you look at a process, if you look at a two-variable process will probably give you a response like this. If you plot the contours of it, and if you project them vertically downward, the contours may look like this. And of course, if you get a 3D picture of the thing, you'll see the dome there. Now, this might be the real process, but I have no real idea that the process actually is like this. What I'd like to be able to do is, I'd like to empirically reach this peak there. This is what I'd like to be able to do. I'd like probably I'll start somewhere around here, or I may start somewhere there. I should be able to slowly climb up to this point. This is what I'd like to be able to do. If I'm able to do that, I'll be able to optimize, find the optimum settings for this design variable 1 and design variable 2. If I'm trying to do process design, I should be able to reach this point empirically, and that's actually the goal of response surface method. Let's see how we end up doing it. We'll take an example, and we'll take an example of a chemical process where yield is the performance. So instead of the etching situation that we had before, remember, I'll have a different cause and effect diagram. I'm just going to draw a sketch of it. I'll have a fishbone drawn again, and I'll have in this case yield as one of the variables. And as far as the process factors are concerned, those are going to be reaction time, and the other factor is going to be reaction temperature. These are going to be my two control variables. And what I'd like to be able to do is I'd like to maximize yield. This is my objective. And I'd like to do this empirically. I'd like to do this empirically by running a series of experiments. This is what I'd like to be able to do. So I'll be climbing a hill. I'll try to climb a hill, and let's see how we do that. I have these two process variables, process variable 1 and process variable 2. Let's see how we climb that path there. This is the real response. And in this case, notice here I've got two variables. I've got time there. I've got time on this axis here, and I've got temperature on this other axis here. The real process is like this. My God, if you look at that, you'd say, how am I going to be studying this? Well, unless I have the theoretical equation for it, it's not going to be easy for me to optimize this process. That's going to be pretty well impossible. How do I then go about doing this? Well, what I do is I'll start somewhere. And then I'll apply the technique of RSM, and that will let me slowly rise up to this point and come up to the peak. It will avoid falling into traps and everything because the RSM technique is a pretty fancy method. And it will require me to run some experiments in the neighborhood of the point where I'm searching. And I'll try to find the direction in which values are climbing. And let's see how we end up doing that. The goal is going to be, if there is a peak, discover that and find basically the process settings that correspond to that particular peak there. This is something I'd like to be able to discover. I'd like to find out at what setting of the process variable 1 and process variable 2 my response peaks. This is what I'd like to be able to do. If I'm able to do that, I'm really able to optimize the process. This is what I'd like to be able to do. So I would like to be able to develop a continuous curve or a surface that will model the response, of the parameters. Let's first take a look at some of the possible models. The first order model, which is a simple linear model, of course, is the one that involves two variables. It has a shape like this. It could also involve the interaction. Now, this is just going to be a main factor, first order effect. If there is interaction, I'll probably have this interactive term also. Once I have this, of course, then it's pretty easy for me to, once I have these equations available, I can apply a lot of different optimization methods, including something as simple as calculus. I could do that. And what do these look like? Well, this is the first order model. You can actually see the shape of it. Now, this is sort of like for a known surface, I could plot this graph, and response is rising this way. So, in fact, if I have to optimize the process, I'll slowly have to somehow climb this way and be able to do that. I'm just showing it to you pictorially. If I have an interaction combined, this is again a first order model, and if I combine an interaction term with it, there is some non-linearity that comes in. And notice here the curvature. Notice here the curvature of the thing. And this again is the thing. Now, what I'm really doing is I'm sensitizing you to the fact that when I've got non-linearity involved, it's no more an easy surface to optimize. It's going to be some pretty complicated. And certainly, if you look at some of these second order models, they have very complex behavior. It's not going to be easy to visualize how they move. Let's take a look at some of these second order models. Eta, which let's say I'll call this the yield, equal to 50 plus 8 times temperature, plus 3 times time, plus minus 7 times the square of temperature, minus 3 times the square of time, minus 4 times temperature and time. That's going to be my response model. It's a second order model because we've got these terms there. The general representation, of course, is going to be something like this. The general representation of a second order model. And now notice, this is not something as simple as these guys, but I could really optimize that. Once I knew what it was, I could do it. This is going to be more involved. how do I do that? Well, one of the ways to do that is to build what we call a regression model. We have to build a regression model, and for that some matrix algebra is involved. And what we end up doing is we have responses that we calculate. We involve a bit of matrices. We'll have a vector for y, we'll have a vector for x, and we'll end up with basically some parameters, beta 1 to beta k, and we'll end up finding the responses using the model there, and the model is shown here. This is going to be one particular type of regression model. If I do that, I may end up with a model like this. Now, how do I construct this model here? I have to really obtain for various settings of x, which now involves k variables. I'll have to vary them over the space, over the range of which x1 can vary, x2 can vary, x3 can vary, and so on. And for each of these points there, I'll have to observe y. So I end up with a collection. Of observed data. This is what I subject to multiple regression. And I'll end up with a model which will be like this. Once I have this second order model, then of course the surface is going to be like this, and I may end up finding the optimum. That would be easy. But of course I'll have to do experiments to be able to find these parameters. That's going to be a big challenge there. This is like another variation of the response surface. This again is the product of a lot of experimental work. Then of course you end up constructing this. If you look at other variations, this is a third variation of a response surface. And notice this one has something that we call a saddle point. It's rather important for us to realize that not all response surfaces are simple to visualize. Some of these have special mathematical structure. How did I develop the surface? I developed that by collecting real data, again in a matrix structure, by conducting experiments, special experiments. For example, one particular approach is called the Box-Benken model, the Box-Benken experiments. These experiments we conduct, those lead to a response surface, the generation of a response surface. They help you determine the different parameters, the beta 1, beta 2, beta 3, and so on. Once you have them, you end up with a surface like this. I've given you a couple of references. I've given you some responses which you can actually see. These references are there. I'll leave them on the screen for you. You can click on them, you can go into more details, and you'll end up finding a lot of things. So to summarize, we reviewed DOE today. We had two sessions. One dealt with finding the main factor effects and the interactions. Then the second one worked with a noisy environment, which was sort of like this. This is the noisy environment, and there we utilized the technique of ANOVA. The third method that we looked at was this technique of response surface, where you end up with surfaces like this. And that can actually help you optimize the process, which is otherwise very difficult to optimize because you do not have theoretical equations for these surfaces, and you cannot really optimize them given the shape of it. We'll continue with this. All this is our march towards Six Sigma. We'd like to be able to reduce defects. We have to understand how these different processes work, and then do something about controlling those control factors and also perhaps control noise, either to make the process robust or to try to improve the performance of the process so that most of our production comes well within the tolerance that is acceptable to the customer. This is what we'd like to be able to do. That is really the goal of Six Sigma. So DOE turns out to be a real important step to move towards Six Sigma. And DOE, as I had told you earlier, if you look at the Six Sigma process, DMAIC, define, measure, analyze, improve, and control. It is the ith step where you utilize design of experiments. We'll continue with this in the next sessions. Thank you very much.